In our today's lecture, we're going to talk about measures of positions and outliers. The objectives are, by the end of this section, we will be able to calculate z-scores and explain why we use them, detect outliers using a z-score method, find percentiles and percentile ranks for both small and large data set, compute quartiles and the interquartile range. Z-score is one of the most important concepts in a statistics class. So we will learn it today and probably we'll keep using it for the rest of the semester. Why z-scores? Z-scores is a way of explaining the location of a data in terms of standard deviation many distances from the mean. Think in a little different and a little innovative way. Oftentimes, when you ask for the distance to the local grocery store from a place you were visiting recently, the people will answer that question in terms of number of blocks. For example, you ask someone, how far is the nearest Kroger from my hotel? And the manager in the hotel tells you, well, it will be around 4 blocks from here. So when you use those type of answers to talk about the distance of a location from a different location, you are using other parameters than our usual concepts of feet or yards or miles. Z-score is exactly that. Instead of using the deviation or the distance of a data from the mean, we talk about the distance in terms of standard deviation. We can say this data is 1 standard deviation away from the mean in the left hand side or in the right hand side and such. So what is a z-score? The z-score for a particular data value from a sample size is given by data value minus the mean. So you find the deviation of the data divided by the standard deviation. So x minus x bar over s, where x bar is the sample mean and s is the sample standard deviation. The z-score for a particular data value from a population is data value minus mean, so x minus mu, because we are in a population, over sigma, where sigma is the standard deviation. Given a z-score, to find the associated data value x for a sample is x equal to z-score times the standard deviation plus the mean, so z times s plus x bar. For a population, it is x equal to z times sigma, the standard deviation, plus mu. And this process is called reverse standardization. So the two processes, if you are given with x, that's called the raw data. So the raw data is in x. To go to z-score, you use the formula z equal to x minus the mean. In a sample, it's x bar. In a population, it is mu over the standard deviation. So in a sample, it is s, and in a population, it is sigma. But if we are given with the z-score and we want to go to the raw score, then the formula is, you say x is equal to z-score times the mean plus the standard deviation. And as I said, this process is called the reverse standardization. Actually, I should have said it's the z-score times the standard deviation plus the mean times standard deviation plus the mean. So let's see how we can use them. Our example 1 is asking us, what does it mean for a z-score to be positive, negative, or 0? So positive z-score. It means what? It means x minus x bar is greater than 0. Means x is greater than x bar, means the data is on the right hand side of the mean, or the data is greater than the mean. Similarly, if you have negative z-score, then x minus x bar is less than 0, which will imply x is less than x bar. So it means the data is on the left of the mean. Whereas if the z-score is exactly equal to 0, that clearly suggests that x minus x bar equal to 0, which means x equal to x bar. So we say the data is equal to the mean. Let's go to example number 2 and explore. Suppose the mean blood sugar level is 100 milligram per deciliter. So as soon as I have read that, I will say that mu is 100 milligrams per deciliter with a standard deviation of 10 milligrams per deciliter. So sigma is 10 milligrams per deciliter. Benjamin has a blood sugar level of 135 milligram per deciliter. How many standard deviation is Benjamin's blood sugar level above the mean? So what do I say? So Benjamin's blood sugar level is 135. The mean is 100. So the question is, how many standard deviation is Benjamin's blood sugar level above the mean? So I divide by the standard deviation 10. So I get 35 over 10, which is 3.5. So basically I found the z-score. And I say, thus, Benjamin's blood sugar level is 3.5 standard deviation over the mean. Okay. Question, then the next question is asking us, Chelsea has a blood sugar level of 125 milligram per deciliter. Question A, if we calculate Chelsea's z-score, what is the scale? Z-score is the standard deviation scale. It is the distance in the scale of the standard deviation. You are talking about the distance in terms of standard deviation. The second question, B, is asking you calculate Chelsea's z-score. So we'll say z-score for, say, Chelsea. Remember, her raw score is 125. Mean is 100, and I divide it by 10. So I get 25 over 10, and that's 2.5. So that's Chelsea's z-score. Interpret her z-score. Well, this is positive. So we say Chelsea has a blood sugar level (2.5 standard deviation over the mean. So it is more than the mean, so over the mean, because it is positive z-score, it is on the right hand side, or more than the mean. Find the blood sugar level associated with a z-score of 2. So now you know the z-score, and you are going to find the blood sugar level associated with the z-scores 2. So z is equal to 2. That means x will be equal to z times the standard deviation. Remember, that's 10, plus the mean, which is 100. So it's 20 plus 100. That means it's 120 milligrams per deciliter. Answers my question. Once business school had a mean quiz score of 60 and a standard deviation of 15. So I am talking about the student 1 who is in business school, and the mean of the business school is 60, the quiz score, and the standard deviation in that school is, in this quiz, is 15. Whereas there is one other student, Louis, and he is in business class as well, and his mean quiz score is 70, and the standard deviation is 2. Both Juan and Luis got a 76. So both of them, their scores, both of them are 76. But clearly they're in two different classes. I want to know who did better related to this class. Let's see that. What I will do, I will try to see how far their scores are from the mean in terms of standard deviation. So we'll say, let's find the z-score of Z1. And the z-score of Z1 is going to be the raw score, which is 60, minus, the raw score is 76 for Z1. He scored 76, minus the mean of 60 over the standard deviation of 15. So it is going to be 16 over 15, and we can use our calculator to simplify this number. So we'll get 16 divided by 15, and that's 1.0667. Rounded to 4 decimal places, it is 1.0667. Whereas when I'm calculating the z-score, the distance of Z1's score from the mean in terms of standard deviation is 1.0667. But the distance of Louis, his z-score, in terms of standard deviation from the mean is his raw score 76 minus the mean this time is 70 over the standard deviation of 2. So this is 6 over 2, and that's 3. And since 3 is greater than 1.0667, I will say Louis has done relatively better. Okay, let's carry on, and this is going to talk about the distribution of data, including outliers. An outlier is an extremely large or extremely small data value relative to the rest of the data set. It may represent a data entry in error, or it may be a genuine data. One way of identifying an outlier is to determine whether it is farther than 3 standard deviations from the mean, that is, its z-score is less than 3 or greater than 3. So in course of doing that, we are also going to describe the class of data. If a data is between -2 and 2 z-scores, or -2 standard deviation to the left to 2 standard deviation to the right, then we call all these data usual data. So think about the mean is a central tendency. So your mean is here. If you are here, this is z-score -2. So I can say that this is the mean x bar. So let me change the mean by x bar, easier to understand. If this is the mean, so x bar minus 2 standard deviation and x bar plus 2 standard deviation. Any data exclusive of these boundaries are called usual data. If your data is between -2 and 3, -3 and 2 and +3, then that is called moderately unusual. So we'll go a little far. This is x bar plus 3s. So again, z-score. So this is x bar minus 3s. So this portion, again, this time you are taking this is closed, but this one is open. So you call this one, and this is closed, and this one open. Those two are moderately unusual. And if you find any data that is greater than or equal to the z-score of 3, or less than or equal to the z-score of -3. So now you're talking about the data that starts here and go there. Starts here and go this way. All these data are called outliers. So of course, we are associating this with a question from the part 1. Determine whether Chelsea or Benjamin had blood sugar level is an outlier. So remember, Chelsea, her blood sugar levels z-score was 2.5. So that's between 2 and 3. So this is moderately unusual, but it's not outlier. Whereas if I do the blood sugar level of Benjamin and find his z-score, that was 3.5, so that is greater than 3, so this is an outlier. There are 2 different ways of understanding the location of a data, and these ways are called percentile and percentile rank. What is a percentile? Let P be any integer between 0 and 100. Then the pth percentile of a data set is the data value at which P% of the values in the data set are less than or equal to this value. Whereas the percentile rank of the data value X equals to the percentage of all values in the data set that are less than or equal to X. So let's try to understand these two things with the following example. Use the following set of stock prices in dollars for the following exercises. So first and foremost, we're going to rewrite the stock prices in order. So see, the lowest stock price is 4, then I have 5. So then I will have 7, and then I have 8. I have 9. I have 10. Then I have 1, 2, 12s. And I have 14, 15, 18, and 20. Let's go with that. So how many total data we have? We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So I'll say total data is 12. And we're finding the 50th percentile. Find the stock prices representing the indicated percentile. So 50th percentile, and this is how I do it. You always remember 50th percentile is referring to 50%. So what do you do? You say that's 50% of the sample size 12, which is 0.5 times 12, and that's 6. So that means I will be able to count 6 data, and that will be the 50th percentile. So let's count it. I will have 1, 2, 3, 4, 5, 6. So that's 10. So according to the definition of percentile, 10 is the 50th percentile. So this is 10. Now we're going to find the 75th percentile. It's similar process. We will go ahead and say that 75th percentile is 75% of 12, which is 0.75 of 12. And that is going to be the 9th data. So we're going to count the 9th data. So that will be 1, 2, 3, 4, 5, 6, 7, 8, 9. So that is 14. 25th percentile. That is 25% of the sample size. So 0.25 times 12. And that should be equal to the third data. So we'll go ahead and say this is 4, 5, and 7. So that's the third data. So it is 7. And there is one more. This time you're finding the 10th percentile. Remember, in the previous 3 situations, we got a whole number as our answer. But if you do the 10th percentile, it is 10% of 12. So that is going to be 0.1 times 12, and that's 1.2. Our job is to always round up. Doesn't matter. We always round up. So we call it the second data. And the second data is 5. So that's the 10th percentile. On the other way around, we are now finding the percentile rank of the stock prices. So 12th percentile rank. What I do? I find number of data that are less equal to 12, divide by the total number of data, and I make it a percentage and round always to the nearest, or to the next whole number, round up. So times 100, and I will say round up. So let's see how many data are there less equal to 12. So we're counting 1, 2, 3, 4, 5, 6, 7, 8. So there are 8 data that are less equal to 12. So I will say 8, total number of data is 12, and this is 100. So you get to say, when you cancel the top and bottom by 4, you get 2 over 3 times 100. So that is 66.6667, which I will round up to 67 percentile. So the percentile rank of $12 as the stock price is 67th percentile. Then I'm going to do it for $20. So number of data, the same thing. That is less equal to 20 over total number of data times 100, and you are always going to round up. So you will get, well, all 12 of the data are less equal to 20. So all 12 of them over all 12 of them, and then you multiply 100, so clearly you get 100%. So the $20 is the 100th percentile in the percentile rank. Finally, we will talk about the quartiles. The quartiles of the data set divide the data set into 4 parts, each containing 25% of the data. The first quartile, Q1, is the 25th percentile, or it is called the median of the upper half of the data. The second quartile, Q2, is the 50th percentile, and it is the median of the entire distribution. And the third quartile, Q3, is the 75th percentile. It is the median of the lower half of the data. The interquartile range is the difference between the quartile 3 and the quartile 1, and is represented by IQR. So IQR is Q3 minus Q1. The interquartile range is interpreted to be the spread of the middle 50% of the data. When the data are quantitative and the frequency distribution is roughly symmetric, the desirable measure of variability will be the standard deviation. And when the data is quantitative and the frequency distribution is skewed, the desirable measure of variability will be the interquartile range. So for the last situation, find the Q1, first quartile, Q2, second quartile, Q3, the third quartile, and calculate the IQR of the above distribution. So let's see, Q1, we already found Q1 is the third data of the distribution, and that number was the 25th percentile, so 7. Q2 is the 50th percentile of the distribution, so that was the 6th data of the distribution, and we found that to be 10. Finally, Q3 of the distribution was the 75th percentile. That's the 9th data of the distribution, which was 14. So it's easy for us to find the IQR now. So the IQR is the interquartile range, which is Q3 minus Q1, and that's 14 minus 7, which is 7. So this is the way that we have learned today. But also remember, if you think of the quartiles as the median, then you will have a slightly different values, and I want to show you that work too. So I will rewrite this distribution one more time. It is 4, 5, 7, 8, 9, 10. The stock prices. 4, 5, 7, 8, 9, 10, 12, 12, 14, 18, or I think it was 14, 15, 18, and 20. So the reason I'm writing it, because now I'm willing to find the medians, appropriate medians, in order to associate them with the quartiles. So remember, the total number of data is 12. So since the number of data is 12, and that's even, the median of the entire distribution, which is the 50th percentile, we just talked about it, and that's your Q2 as well, should be equal to, let's do 12 plus 1 over 2. That's what we have been doing. So 12 plus 1 over 2 at data, and it will not be a real location, so we have to be a little innovative. So 12 plus 1 over 2 is 13 over 2, and that's 6.5. So 1 on the left of 6.5, 1 on the right of 6.5. The left of the 6.5 is the 6th data, and the right is the 7th data, so we find both of them. The 6th data is, of course, 10, the 7th data is 12. I add them, divide by 2. This is our usual way of finding the median. So I get 22 over 2, and that's 11. So this is your quartile 2. Quartile 2 is 11. So what we will do now, using this same process of finding the median, we're going to talk about the quartile 1 and quartile 3. So think about the distribution. If you have put in this median of 11 here, so that's the median location, then this is the lower half of the data and this is the upper half of the data. Quartile 1 is the median of the lower half of the data. So lower half, this distribution has the size 6. Again, it's even. So what I do? I find the median by doing 6 plus 1 over 2, that's 8. So that's 7 over 2 and that's 3.5. So on the left, you have the third position. On the right, you have the fourth position. And the third data of the distribution is 7. The fourth data of the distribution is 8. So I do 7 plus 8 over 2 as quartile 1, the median. So this is the 25th percentile. So this is 15 over 2 and that's 7.5. Similarly, for the upper half, I don't have to repeat this work because it has the same sample size. So you look at the upper half and you find the third data and the fourth data and divide by 2, and this is going to be the 75th percentile, which is quartile 3. So what is the third data in the upper half? Well, that's going to be 14 and the fourth data is 15. So I'll say it's 14 plus 15 and that's 29 over 2. So 29 over 2 is 14.5. So that's Q3. So the interquartile range in this situation is Q3 minus Q1, which is again, if I do Q3 minus Q1, I don't get a surprising result. It's 14.5 minus 7.5 and it's still 7. Answers my question.